in this section P.3, we're going to cover everything related to radicals and rational exponents. It's going to be an overview of the radicals. Now, let's go ahead and start with a couple of examples of the radicals and what a radical is, first of all. So radical, basically, this is what the radical sign is. This is what the radicand is called. And there's another part of the radical that it's going to be mentioned a little bit after, which I'm going to mention already, which is going to be what is called the index. The index is the power of that radical, okay, which is going to refer to it afterwards. So what does a radical mean? So it's first thing you're gonna be going over the definition. It means that we're looking for a number, some number b that we don't know, so that when I raise it to that n power, which is the index, it equals to the number a inside of the radical. Okay, so that's basically what we're looking for that number b, that when raised to that n power, it equals to that number inside of the radical. Let's go ahead and cover a couple of examples on the radical, which we're going to start with these two special examples. We're going to evaluate the following expressions or state that the root is not a real number. So this negative on the outside right here basically means the following: -1 times the square root of 100. So in this case, so whatever the square root of 100 is going to be multiplied times -1. That's what this one basically means. And what is the square root of 100 means? It means that we're looking for a number that when we square it, now that is one thing that I need to mention here. You see that this radical does not have an index. That by definition means that the index is going to be an index of 2 if it doesn't have one. Okay, so that's why I say the second power. So we're looking for a number that when raised to the second power, it equals to 100. And that number is going to be a 10. So that's the square root of 100, 10. Then if I multiply times that -1, the answer is going to be -10. So keep in mind, when I have a negative on the outside of the radical, all you're going to do is you're going to bring the negative, you're going to carry the negative in front of the radical at the end. Okay. Now, in this second case, it is a little bit different, because what we see is that still it is a square root, because the index is 2. But what are we looking for? Look, the negative is inside. So that means that we're trying to find a number that when I raise that number to the second power, it gives me an answer of -4. Now, just be careful, because keep in mind that if I raised 2 to the second power, gives me 4, but how can it give me a -4? What if it is a -2? Does -2 to the second equals -4? No, because if I multiply -2 times -2, it's also going to equal a +4. So it doesn't work. So what does that mean? That any time the square root has a negative number in the inside, this number is going to result, or the solution for this is that it is going to be not a real number, because we won't be able to find the square root of that number. Now, let's work on a couple of more cases on radicals before we come back to all of those things that we're going to talk about. Now, the next thing that we're going to discuss is now this other radical. Now, this radical right here represents a cube root. On this one, we are trying to find, this is a -216, so which means we're trying to find a number that when I raise it to the third power, that's my index, it equals to -216. And if you think about it, -6 times -6 times -6 is going to give me -216. So that means that the cube root of -216 is -6. Now let's do one more example. We're going to work on this last one here. This is the fourth root of -1. What does this one mean? This means that we're looking for a number that when I raise it to the fourth power, it gives me a -1 as an answer. Can I say that negative 1 to the fourth power gives me negative 1? No, because negative 1 times negative 1 times negative 1 times negative 1 is going to equal to a positive 1. So this doesn't work. So once again, since I have a negative on the inside right here, this is not a real number. So let's do a little summary of when is it going to happen that the root is going to give me not a real number. Based on the two examples that I show you with no real numbers, you can see that whenever we have a square root of a negative, it resulted into not a real number. Whenever we have the fourth root of a negative, then it resulted in not a real number. So as a fact, anytime I have an even root of a negative number, the answer for this is automatically going to be not a real number. Okay, so the next item. So the next item in the agenda is that we're going to be simplifying radicals using what is called the product rule. Okay, so the product rule tells us that the square root of a times b equals the square root of a times the square root of b. Likewise the other way, the square root of a times the square root of b equals the square root of a times b. So what we are going to do in the next problem is that we are going to simplify radicals that are not perfect squares by factoring. So the problem is the square root of 54. So that's what we want to simplify. Now 54, there's nothing that I can square that will give me a 54. So in this particular case, what we have to do is we need to factor this radical. Now there are two ways that we can do this, which is one of them is by a factor tree, and then we get when we get the square root means we need to get pairs of the same number. That is one way that we can do it. So I'm going to show it to you both ways. So let's start with the factor tree. So this is what we would do using the factor tree. So we're going to say 54. We can break it down into this. It's going to be 2 times 27. Then 27 now can be broken down into 3 times 9. And 9 can be broken down into 3 times 3. So you see that there is a pair of 3's right here in this expression. Now if we write this number, square root of 54 is going to be the same as square root of 2 times 3 times 3 times 3. But the square root means we need to get a perfect square. A perfect square means a pair of the same number. So that if we get this pair, that is going to simplify to a 3 outside of the radical, because that's 3 times 3 is 9, but the square root of 9 equals to 3. So that radical simplifies, and then the leftover we're going to keep it inside of the radical, which is 2 times 3, and that is going to be a 6. Now this is one of the ways that we can simplify a radical, by taking out the pairs whenever it comes to a square root. Now there is another way that we can use to simplify a radical. We can factor it in a different way, which is this. Now what we need to do is we need to get a factor, the greatest possible factor that is a perfect square, and it's a factor of 54. So from the perfect squares we can say there's the following factors. We have 4, we have 9, 16, we have 25, 2 squared, 3 squared, 4 squared, 5 squared, then 6 squared, 7 squared, and then 8 squared is 64, which is above 54 already. So now one of these factors, we need to find out the largest possible factor that is a factor of 54. In this case 49 is not a factor of 54, because 49 times nothing equals to 54. 36 is not a factor of 54, likewise 36 times nothing equals to 54. 25 is not a factor of 54, because 25 times nothing equals 54. Then we got 16 times nothing equals to 54, and if you look at the 9, that one does. 9 times 6 equals to 54. So 9 is a factor, so that's the largest possible factor. So we can break it down into 9, square root of 9 times 6 and according to the product rule, we can separate it into the square root of 9 times the square root of 6. And the square root of 9, this is going to give us a 3, and then the square root of 6 is just going to be carried over. So that's 3 square root of 6, which gives us the exact same thing. It is just a different way of finding, simplifying a square root. Now, we're going to do an application that requires simplifying square roots as well, which is going to be adding and subtracting radical expressions. Now, to add and subtract radical expressions, we need to ensure that the two radicals have the same radicand, meaning the same number inside of the radical. Okay, so they need to have the same radicand in order for them to be added or subtracted. And the only thing we add and subtract is the coefficients. 7 square root of 11 plus 6 square root of 11, we just combine the coefficients, 7 plus 6, that's 13 square root of 11. So the radical is going to stay the same. You're going to combine them as if they were like terms. But in this case, we call them like radicals. That's how addition and subtraction is performed. Okay, so now let's go ahead and add these two 4 radical expressions in this problem. Now the first thing we got to do in this radical expression, of course, is going to be to simplify with either one of the two methods that I explained before. So I'm going to use the perfect squares method that I showed previously. Okay, so for the perfect squares, we got 4, 9, 16, 25, 36, 49, 64, and then that's as far as we need. The next one is 81, which goes over these values right here. So we need to find out again to simplify the square root of 12. Well, first of all, before I do simplify it, I want to mention this. This 3 square root of 12 means 3 times the square root of 12. Okay? So this is going to be 3 times, and then we need to simplify the square root of 12 by factoring. So right here, which one of these two multiplies to 12? So we can check on all of these, but the only one is going to be 4. So when we multiply 4 times 3, it's going to give us 12. Right? So that's the perfect square that we're going to use for this. So then we're going to have 4 times and then a 3, which is going to be 12. Then remember, the product rule states that the square root of 4 times 3 is the same thing as the square root of 4 times the square root of 3. And then we can simplify this. So that would be 3 times, and the square root of 4 is equal to 2. So it would be 3 times 2 times the square root of 3. And we can simplify it by multiplying these two values. That's going to be 6 square root of 3. Then we're going to continue doing the same thing for the rest of them. Now there's a minus right here. So the next thing that we're going to do is we're going to simplify the square root of 27, which is going to be the same deal. Now, which one of these is a factor of 27? It's going to be 9. So it would be 9 times 3 equals to 27. So we're going to factor it out into a 9, square root of 9 times 3, which again, we can then separate it into the square root of 9 times the square root of 3. And the square root of 9 equals to 3, so we're going to get a 3 for this, times the square root of 3. Then we're going to continue with the next one. Then we have a plus right here. And the next one is going to be 3 times the square root of 75. So we got 3 times, and then the square root of 75, we can simplify it. We can factor it by 25. So that would be 25 times 3 equals 75. So it's going to give us the square root of 25 times 3, which again we can factor into 3 times the square root of 25 times the square root of 3. And then the square root of 25 is 5, so this is going to be 3 times 5 times the square root of 3. We multiply these two values, which is going to give us a 15 square root of 3. Then to finish, we're going to have again a minus right here, and then we're going to simplify the square root of 72. So we're going to do the exact same thing. Now for 72, now keep the following in mind. There are several factors that can divide the 72, mainly 4, 9, but also 36. When there's several factors, remember what I mentioned to you, you have to use the biggest possible factor. So it would be 36 times 2 equals to 72. So this is the one we have to use because it's the largest. So square root of 72 is equal to the square root of 36 times 2, which now we can separate into the square root of 36 times the square root of 2. And the square root of 36 is going to give us a 6 times the square root of 2. Now, the idea for this problem was to add and subtract radicals. So now we have to determine which ones of these radicals can be added and subtracted, which in this case the answer is going to be that the first 3 can be combined because those are the only ones that have the same radicand. So, and when we combine them, remember we're going to combine the coefficients, the numbers in the front. So if I do that, then 6 minus 3, it's 3, plus 15, it's going to be 18 square root of 3. And then we're going to bring down the minus 6 square root of 2, and this is going to be the answer for this problem. Now, the next thing we're going to cover is going to be the quotient rule, so which deals with division of radicals. So that's going to be the next objective here. Now, the quotient rule for square roots, it states that if we have a square root of a over b, that is equal to the square root of a divided by the square root of b, or vice versa. Square root of a over square root of b equals the square root of a over b in the same square root. Okay? So, we're going to do a very simple question with regards to the quotient rule, which is going to be this problem right here. Use the quotient rule to simplify the expression. So we got the square root of 16 over 9. So that one we can separate it into the square root of 16 over square root of 9, and then we simplify it. The square root of 16 is going to be 4 over the square root of 9 is going to be 3. So it's going to be 4/3. That will be the solution. Okay. Now, let's keep in mind that I'm not going over this information anymore. What does this one mean? We're looking for a number that when squared, it gives me a 16, which is that 4. And right here, we're looking for one number that when squared equals to 9, which is that 3. Okay? Now, let's work on the next thing. There are some cases in which the denominator cannot be simplified. Now, when we end up with a radical on the denominator that cannot be simplified, we're going to use a process called rationalizing the denominator to simplify the radical from the denominator. That's going to be the next topic. Now, this is what rationalizing the denominator consists of. Basically, to rationalize the denominator, which means to get rid of the radical from the denominator, we are going to multiply both the numerator and the denominator by the smallest possible number that will give you a perfect square on the denominator. This is the definition. The process of rationalizing the denominator consists of multiplying the numerator and denominator by the smallest possible number that produces a perfect square in the denominator. So, in this case, we have, like if you look at this example up here, we got 1 divided by the square root of 3. Now, what is the smallest number that I can multiply here on the denominator so that this square root of 3 becomes a perfect square? Well, the easiest case will be multiplied by itself. That's what you see right here. If I multiply this number by itself, it's going to become a perfect square, which is the square root of 9, and that is equal to 3. Now, whether you get a radical on the denominator, that doesn't really matter as long as it is simplified. The only thing that matters is that the denominator cannot contain a radical. So that's what the process is called, rationalizing the denominator, which in other words means getting rid of the radical from the denominator. So let's answer the following question with regards to rationalizing. So the question we are going to do is this. Square root of 11 divided by the square root of 5. So in order for me to rationalize it, I need to multiply the square root of 5 by itself so it produces a perfect square. But we also need to multiply the numerator by the square root of 5. And on the denominator, it's going to be the square root of 5 times 5, which is going to give you the square root of 25. and that is equal to 5 on the denominator. Now, the numerator, it's going to be the square root of 11 times the square root of 5 is the square root of 11 times 5, which is equal to the square root of 55. And now, can the square root of 55 be simplified? You can find a perfect square that can be divided into 55, such as 4, or 9, or 16, or 25, or 36, or 49? The answer is no. None of them divide 55, so 55 is going to stay as it is. And this is my answer with the denominator completely rationalized. Alright, so we're going to go over the last concepts that we need to learn on this section. Mainly, we're going to do the rational exponents. So I'm going to go directly to the general rule of rational exponents, which is this right here. Okay. So what does a rational exponent mean? It is an exponent that is a fraction, basically. And that whenever you have an exponent that is a fraction, that fraction contains two components that I want to mention to you. The numerator of this exponent represents a power, and the denominator of this exponent right here, which is the n, represents a root of the number. So that's what you see right here. If you look at the right side of this equation, it tells me that the m on the numerator means that the number is being raised to the m power, and the n on the denominator means that you're taking the nth root of that number a. That is the definition of a rational exponent. A rational exponent is power over root, anytime we have an exponent in the form of a fraction. Likewise, this is one of the properties of exponents that you need to keep in mind. Anytime I have a negative exponent, the negative exponent represents the reciprocal of the number. So if I want to change that negative exponent to a positive exponent, all I do is this. This number a is over 1. So to make it a positive exponent, all I do is I get the reciprocal of this number. A over 1 becomes 1 over a, and the exponent changes its sign to positive exponent. That's what the negative exponent rule is, does. Let's work on this example on the rational exponents first. Question says, we want to use radical notation to rewrite this expression and then simplify this if possible. So, that rational exponent, remember, according to the definition, the numerator of this exponent represents the power, and the denominator of this exponent represents the root. So basically, that 81 raised to the 1/2 means the following: that you are taking the square root of 81, and then that power of 1 means that you are raising it to the first power. So, if I get the square root of 81, that is going to give us a 9 right here. But then if I raise that to the first power, that is still going to be 9. So, as a summary, what does the 1/2 power basically mean? The square root of a number. Because that 1 power basically doesn't do any change to the number. Keep that in mind. This is one of the general properties that I want you to keep in mind. Anytime I have a number raised to the 1/2 power, that basically just represents the square root of the number. Likewise, if I tell you, okay, I have a number raised to the 1/3 power, that means the cube root of the number. Now, let's go ahead and work out on the following problem, which is also about the same thing on rational exponents, but the exponent is negative on this time. This is a 125 raised to the power of -2/3. So, the very first thing that we must do is that we need to make that exponent a positive exponent. In order for us to do that, remember that this 125 is over 1. So to make that a positive exponent, all I gotta do is take the reciprocal of this number, which is going to be 1 over 125, and that it's going to make that exponent to become a positive 2/3 exponent. Then we're going to go through the properties of rational exponents, which means that the numerator of this exponent represents the power and the denominator of this exponent represents the root. So that 125 raised to the 2/3 power means that you are going to get the cube root of 125. So let me give myself more space. Cube root of 125, and then at last you are going to raise that answer to the second power. So first of all, let's get the cube root. What does it mean by this? We're trying to find a number that when cubed equals 125, and that number is 5. Right? So I'm going to simplify that. So on the denominator, we're going to get a 5. But then we have one more thing to do to it, which is raised to the second power. And my final answer for this is 1/25, or 1/25. Now, we are going to review really quick the properties of exponents that you're going to be using in chapter 4 later on in the semester. Now, this is just a quick review of the general properties of exponents that you're going to be using. First of all is the product rule. The product rule states that if you have a base raised to a power times the same base raised to another power, then you're going to add the powers. You're going to combine them into additional powers. Now, the second one is called the quotient rule, right here. The quotient rule. The quotient rule states that if you have a base raised to a power and you divide it by another base raised to another power, to the same base raised to another power, then you subtract the powers. And the third rule, it is called the power rule of exponents, which tells us that anytime I have any base raised to a power and that is being raised to another power, then you multiply the powers. Okay. This one, power of a product and power of a quotient, these are combinations of the power with product and power with quotient rule. So what does this basically tells you is that if you have a product, which is a multiplication of several bases, raised to a power, then you're going to distribute the power to every power of that product. Now, the second rule, which is the power of a quotient, states that if I have a quotient of several bases and raised to a power, then you're going to do the same thing. You're going to distribute the power to every power inside of that quotient. And we have two more rules. One of them is the negative exponent rule that we talked about, that anytime I have a negative exponent, that represents the reciprocal of the number. And then there's one last rule, which is the zero exponent rule, that anything raised to the zero power, regardless of what is being raised to the zero power, that is always equals to 1. Now, let's go through some of the properties of exponents in the following questions. First question is, simplify using the properties of exponents. We got 3x raised to the 1/2 power times 4x raised to the 1/5 power. First thing is going to be, we are going to multiply these two numbers right here. This is just regular multiplication. So it's going to give us a 12. And if I want to combine those two x's, since they're multiplying, then what I have to do to combine them is, I need to add the powers. Now the thing is that since these two have different denominators, what I have to do is find the least common denominator. So 2 and 5, the smallest number that they can be multiplied to is going to be a 10. So that means that I need to make both denominators become 10s. So to make this one a 10, I need to times it by 5, and I do the same thing for the numerator. So that's going to give me a 5/10 for the first exponent. And to make this a 10 on this denominator, I need to times it by 2, and I need to do the same thing to the numerator. So that would be a plus 2/10. And if I combine those two exponents, 5/10 plus 2/10 is going to give me 12x to the 7/10. And this is the solution for this product rule. Next, now we're going to work on this problem about the quotient rule. This is going to be very similar, but now we're going to apply the quotient, which tells me that anytime I have a quotient of two of the same base, then I have to subtract the powers. For these two numbers, we're going to do regular division. So just divide them out. 28 divided by 4 is going to be a 7. And then the x's, or those bases, in order for me to divide them, we have to subtract the exponents. So it would be x to the 1/4 minus 1/6. Now we have to think of what would the least common denominator is right here. What's the smallest number that 4 and 6 can both be multiplied to? And that would be a 12. They can be multiplied to 12. So that means that I need to make both the 4 a 12 and the 6 a 12. So how do I make the 4 into a 12? By multiplying the 4 times 3. But we also have to do the same thing to the numerator, which is going to make it a 3/12. Now, how do I make that 6 a 12? By multiplying it by 2. And we do the same thing to the numerator. So that's going to give us a minus 2/12. So then we're going to get 7x to the 3/12 minus 2/12 is going to be 7x to the 1/12. And this is the solution for this quotient. Next one. Now we're going to use properties of exponents to simplify this expression with the power rule. This is basically the power of a product. Now, keep one thing in mind, that the 32 does not have a power. That means it's being raised to the first power. Right? So the power of a product states that if I have powers raised to powers, all I need to do is multiply this power times each one of these powers. So if I do that, then we're going to get the following. 32 raised to the 1 times 1/5 is going to be 32 raised to the 1/5. Now, x raised to the 25 times 1/5. Then if I multiply 25 times 1 and then over 5, it's going to give me a 5. Then we have the y raised to the 10 times 1/5. 10 times 1 and then over 5, it's going to be a 2. So it's y to the second power. So there is one more thing that we can do in this problem, which is the 32 raised to the 1/5. What's the meaning of that? We talked about that. Remember that the numerator represents the power, the denominator represents the root. So that 32 to the 1/5 basically means that you're taking the 5th root of 32 and everything raised to the first power. Remember that first power is actually not going to do anything, right? It is just basically the 5th root of 32. Now, what does the 5th root of 32 mean? It means that we're trying to find a number that when raised to the 5th power, it equals to 32, and that number is going to be 2 to the 5th power, right? So the solution for this problem, it is going to be 2, which is the 5th root of 32 is equal to 2, and then x to the 5th power, y to the 2nd power. And that's the solution for this power of a product rule. Last question on this section is going to be this one. We're going to simplify this expression by reducing the index of the radical. This one says 10th root of x to the 8th power. Now let's remember what this means. The 10th root of x to the 8th power, we can rewrite it as an exponent, and the exponent would be power divided by root, which is 8/10 power. So all we gotta do here is this fraction, we need to reduce it. So for 8 and 10, we can divide them by 2, and that's gonna give us a 4/5. So this is the same thing as x raised to the 4/5. And then we can put it back as a radical. That means the x raised to the 4/5 means the 5th root of x to the 4th power. And this concludes section P.3, which is radicals and rational exponents.